The central limit theorem states that given a sequence x1, x2, x3, and so on of IID random variables with a finite but non-zero variance, that if we take the partial sums of the sequence, the sum I equals 1 to n of the xi, and subtract the mean, and divide by the standard deviation, then for large enough values of the sum, we're going to have approximately a standard normal distribution, meaning a normal distribution with mean 0 and variance 1. So this is the way to formally write that if we take the limit as n goes to infinity, this probability eventually converges to the probability that standard normal is less than a number t, where this z is just a standard normal. And if we divide through by n on the top and bottom, we can rewrite the formula as the average of the first n numbers minus the average of any one of them divided by the standard deviation. So let's look at least a sort of an intuition of why this might be the case. So for any fixed n, x1 plus x2 plus up to xn has mean n mu, because each xi has mean mu, and the expected value is linear. So whenever we have n of them, the expected value of the sum is just the sum of the expected values, and they're all mu. So this is n times mu. Also, because the random variables are independent, the variance of the sum x1 through xn is the sum of the variances. Each random variable has variance sigma squared, so the variance of this sum is n sigma squared. And therefore the standard deviation is the square root of n sigma squared. So this formula here that's inside the formula for the central limit theorem is the partial sum minus its mean divided by its standard deviation. And if we look at the running average, so the average of the first n variables, the expected value of this is also mu by linearity of expected value. So the 1 over n comes out, and this is n times mu over n, which is mu. And similarly, the variance of the sum is the sum of the variances. So this 1 over n here, that's a constant, that becomes squared, so it's 1 over n squared, times the sum from I equals 1 to n of the variances of the xi's. Then this is 1 over n squared times n sigma squared, because there's n of these variables. They all have variance sigma squared, and the n cancels, so we get sigma squared over n, which means the standard deviation of the running average is the square root of sigma squared over n. So there's another lesson on the strong law of large numbers, which cancels out all the randomness, and it shows that a random variable will, a running average of random variables will converge to the mean with probability 1, so that eliminates the randomness. In this case, we divide by a certain number that keeps some of the randomness, but it's a meaningful way. And notice at how broadly applicable this is. No matter what the random variables distributions are, the x1 through xn, as long as the variance is between 0 and infinity, this is going to behave like a standard normal random variable. So we've got a table here that's used for reading probabilities for a standard normal. And I've just copied this over from the lesson on the normal distribution. So this is introduced in the normal distribution. Let's look at a couple of examples of the central limit theorem. So let's say that a standardized test was given to all 12-year-olds in the United States, and the average score was an 83.1%, and the standard deviation is 3.2. What's the probability that a random student scores above 90%? So to do this problem, we're going to make a couple of assumptions. The first is that there's a lot of 12-year-olds in the United States, so whenever we approximate the scores of all the 12-year-olds, we can approximate it with a standard normal. Also, we're going to assume that we're just randomly choosing a student among all students. So they could be a strong student or a weak student. It's equally likely to get any student. And finally, we're assuming that the performance of the students is somewhat independent of one another. So under those assumptions, the probability y, which we'll say, well, let's define y as the score of the randomly chosen student, and the probability y is above 90 is the same as the probability y minus 83.1 over 3.2 is bigger than 2.15625. So the reason I'm scaling that out is because I'm subtracting the mean and dividing by the standard deviation to normalize the random variable. So this is approximately the probability that a standard normal z is bigger than 2.15625. And the probability that a standard normal is bigger than 2.15625 is equal to 1 minus the probability z is less than or equal to 2.15625. And for this probability, we can go to the table. So we're looking at the most accurate we can get with the table that I've included is 2.15. So if we go to the table, we're looking at 2.1 in the row, and then the 0.5 in the column, which gets us 0.98422. So coming back down, we get 0.98422, and then we're looking at 1 minus that, so we get 0.01578. So there's roughly a probability of 0.01578, or about 1.5% chance that the student scored above a 90, because about 1.5% of the students who took the test will have scored above a 90%. Next, we're going to take a slightly less obvious example. We're going to have a binomial random variable with parameters 1,276 and 0.7. So remember that 1,276 is the number of trials, and each one has a success probability of 0.7 and a failure probability of 0.3. The question is, what's the probability that x is less than 700? And that might not seem like a very strange question to ask, but I want to show that these probabilities are a little less intuitive than most people believe. So a lot of people have this misconception that they have a good intuition about probabilities coming into probability, and then they realize that actually their intuition is pretty poor once they see some examples like this. So x is a binomial, 1,276, 0.7. And if you go to the lesson on the binomial random variables, you'll see that the binomial has the same distribution as the sum of Bernoulli's. So this is the same distribution as the sum of 1,276 IID Bernoulli random variables. So we could rewrite this as the sum from I equals 1 to 1,276 of the yi's. The mean of a binomial, which is the product 1,276 times 0.7, is 893.2. And the standard deviation, which is that number, then times 0.3, is 16.37. So the probability that x is less than 700 is the probability that the sum of Bernoulli's is less than 700. And then we can normalize this. So subtract the mean, divide by the standard deviation, and therefore we can approximate this as being a standard normal random variable. But when we subtract the mean and divide by the standard deviation, we must do that to both sides. So we're subtracting 893.2 from 700 and dividing that by 16.37, which leaves us with negative 11.8. And if you go to the table, you'll notice that the table doesn't even go past 2.99. So negative 11.8 is way off the table. And I even just wrote it's approximately 0 here. If you wanted to see the actual value, I went ahead and computed it. It's 0.000 something, a whole bunch of zeros, and then finally a 19. So it's extremely unlikely that you're going to have a value less than 700, even though the mean is 893.2. And that's because it's 11 standard deviations, almost 12 standard deviations away from the mean, and that's extremely unlikely to happen. Next, let's look at another similar sort of example. So we're going to look at a Poisson random variable with parameter 965, and we want to know the probability that this Poisson is less than 900. So if you recall, for two Poisson random variables, if x1 has Poisson distribution with parameter lambda 1, and x2 has Poisson distribution with parameter lambda 2, and these are independent, then x1 plus x2 has the Poisson distribution with parameter lambda 1 plus lambda 2. So you can sum the parameters. And therefore, if x is Poisson 965, it has the same distribution as summing 965 random variables that are Poisson 1. So we're going to let y1, y2 up to 965 all be Poisson 1. And 965 is certainly large enough that we could apply the central limit theorem. So the probability x is less than 900 is the probability that the sum of 965 Poisson 1 random variables is less than 900. And for a Poisson, the mean and the standard deviation, well, the mean and the variance are both equal to the parameter. So the mean is 965. The standard deviation is the square root of that, so the standard deviation is about 31.06. So we can now normalize this sum, subtract the mean and divide by the standard deviation, and we get negative 2.09. So this is approximately the probability that a standard normal is less than negative 2.09. And to use the table, we need to do a little rearranging. So because the bell curve is symmetric about 0, the probability that a standard normal is less than minus 2.09 is about the same, is exactly the same by symmetry, that the random variable is greater than positive 2.09. So we can change this to the probability z is bigger than or equal to 2.09. And that is going to be 1 minus the probability it's less than 2.09. And we can read the probability that it's less than 2.09 from the table. So let's go to the table and look for 2.09. So now we're looking at the row 2.0, and we're going to 9, so that's the last value. So that's 98.196. And we can plug that in, so we have 1 minus 98.196 equals 0.018, or roughly a 1.8% chance.